Hi everyone, and welcome to our section on power flow in the induction machines. By the end of this session, you should be able to describe the power flow in a three-phase induction machine and calculate the input, output, and loss power in the induction machine using the equivalent circuit. And here we will really be looking at the equations and how they relate to each other, to the parameters in the equivalent circuit and the slip in particular. So what we have here is a diagram showing input power that we apply on the electrical side, the terminals of the machine, and that goes into the stator. And if you remember, we have here a three-phase voltage and current source coming in balanced, and from that we get our rotating magnetic vector. Now, before it gets to that point, in the windings, we're going to have copper losses, I squared R, and we're also going to have core losses, the no-load current squared by the core resistance. This is just like in the transformer, if you remember. And once we account for those losses, the remainder of the power crosses the air gap. This is a small gap between the rotor and stator. Remember, they're not actually connected, because if they were, then you couldn't get rotation. So that the power that crosses that small gap is what we call the air gap power, and that goes to the rotor. And in the rotor, once we're there, we have some copper losses again, which is the slip multiplied by the air gap power. Remember, slip is very small at full load, so a small portion of it goes to the copper losses, and the remainder of it goes into mechanical power. Now, the mechanical power, part of it has to take care of friction and windage. Part of the mechanical power has to actually go to move the weight, the mass of the rotor itself. Remember, it is not an ideal machine where you have zero mass. So before you move any load that you want to connect to the motor, you have to move the motor mass itself, the rotor mass itself. And if you subtract that from the mechanical power, you end up with the net output power, which is the power available to the user. So this is the basic flow of power from one end to the other. So, and if you remember this, you'll have a very good idea of how to manipulate your equations and so on to get the power, the correct power that is being asked in the questions. So just to go it over one more time, we have the input power that goes into the stator. We have the copper losses and the magnetic core losses. The remainder of the power crosses the air gap. That is what we denote by PAG, and some of those losses, the slip, which is given by the slip multiplied by P air gap, goes into the rotor circuit where it's dissipated as heat in the rotor windings. The rest of it, 1 minus slip multiplied by the air gap power, goes into the mechanical power, and some of that mechanical power is used to overcome drag forces and to move the mass of the rotor, and then the remainder is what is available to the user. So if we look at this in an equivalent circuit, we have our power coming in here, which is our P in. We have some losses in the core and then some losses in the stator. Now you'll see here the core losses for the core, V squared and R, the 3 just comes about because it's 3 phases, and these are per phase diagrams. You don't draw line to line diagrams in these equivalent circuits, so they're per phase diagrams. So this is the phase voltage. So when we find the power here, it is the per phase power, and since it's a 3-phase machine, we multiply it by 3. So V squared on Rm, and then we have the copper losses that take place in the stator copper losses, and you'll see this calculated two ways. Sometimes we use I2 and sometimes we use I1. I2 prime, of course, is the current that is from this diagram that is flowing in this branch here, whereas I1 is in this branch. So why the difference in these equations? Obviously, from this diagram, I2 is the one you should use. But remember, in reality, this is a simplification. It is a modification of the equivalent circuit. The original equivalent circuit we developed had the core branch on this side. And if the core branch was on this side, then the current here would be I1. So that is why you get sometimes the I1 being used, sometimes I2 being used. Now remember, just like in the transformer, the no-load currents, the magnetization current here, Im, when the motor is operating at full load, this magnetization current is very small. So I1 would be approximately equal to I2. So using one or the other will not cause a big difference in the results. So I just thought I would mention that because you'd see it in a lot of textbooks. You'd see them being used interchangeably, and sometimes there's not a clear explanation as to what is going on. So just keep that in mind when you're dealing with the equivalent circuits, that you have all these approximations going on in the circuit. Now, after we account for these losses, we're crossing the air gap of the machine. So this is going from the rotor, from the stator, which is on this side here, to the rotor, which is on this side here. So we get into the rotor of the machine through this air gap. And then when we get into the rotor, we have some losses in the rotor, again some copper losses, which is I squared R multiplied by 3 for 3 phases again. And this is also equal to S times the power coming through the air gap. The remainder of the power goes into the mechanical system, and you'll see here I separated stator, rotor, and mechanical system. So this is stator electrical, rotor electrical, and mechanical, right? So the mechanical system here, now we have the power here is I squared R again, which is I2 squared multiplied by this resistance, which is R2 on S multiplied by 1 minus S, which is 1 minus S multiplied by the air gap power. This power contains in it both the friction and windage and the load power, the power that is being used, the power that the user needs to get out of the machine. You can't separate this further because the no load power, the friction and windage and so on would often be considered a constant. So if you try to separate it in two resistances, one to account for the friction and windage and one for the load, the friction and windage would change when the current changes, and that is what you don't want to do in practice for the modeling. So we usually just keep it as a constant. So for all purposes, we're going to leave this as one entity which represents all the mechanical power, and then we will know at full load, based on experiments and so on, what the friction and windage usually is, and we could just subtract it to get the output power. So we described all the power so far in terms of the electrical parameters I and R, but we could also describe these in terms of T and omega. So that same air gap power, we could describe it using the developed torque, and this TD here is the torque developed by the magnetic flux interaction. Remember, the interaction of the magnetic flux gives us a force, and a rotating force is called a torque. So that is all this means here. It is the force developed, that rotating force developed by the interaction of the magnetic fields. And the synchronous frequency is the frequency of that flux, right? So this is the frequency of the rotating flux produced by the stator, not the rotating magnetic field produced by the stator, not the rotor speed. remember the rotor speed will always be a little bit less because of the slip of the machine. So this synchronous frequency refers to the stator frequency. So you could think about it as that, synchronous frequency or stator frequency. So T by omega S. And of course this would be the rotation of the magnetic field. So it's not that it will always be 60 Hertz. Depending on the number of poles of the machine, this could change, because the magnetic field will, the larger the number of poles, the slower the magnetic field will turn, because the more north poles and south poles you'll have in a single revolution. And if you're not sure what I'm talking about, you could go back to the initial video and look at the part about number of poles and how the magnetic flux distribution is derived. So so this is the air gap power, and again part of that power goes into the losses, which is S multiplied by the air gap power, which would be S multiplied by this. The remainder 1 minus S is the power converted to mechanical power. So 1 minus S multiplied by TD omega S, which is the same as TD multiplied by omega. Remember, omega S multiplied by 1 minus S, this would be a value between 0 and 1, like 0.98 or so, would give us the actual mechanical speed. So the developed torque by the mechanical speed of the rotor gives us what we call the developed power. And this is the mechanical power. Sometimes we also call it the electromagnetic power. This is the power that is converted from electromagnetic energy into the mechanical energy that the system, into the energy associated with the motion of the rotor. Some of this energy, goes into friction and windage, and the remainder is available to the user. So some torque, some force has to be used to overcome the rotor mass, has to be used to overcome the friction of the machine, and so on. So we have a reduced amount of torque, and we just remove the D and just leave it as T alone with no subscript, and this refers to the final output torque of the machine. So if you're looking for if you're looking to spec out a machine, this is the torque that you will see, because this is what is available to the user. The others, TD and so on, are internal to the machine. And the output power here is what you would typically see as your horsepower. So just to go back now and bring everything together, you have the input power. On the left hand side here we have the losses, and on the right hand side we have the main power path. So the input power, we minus copper losses in the stator, iron losses in the core. The remainder is the air gap. Then from the air gap, this crosses from the stator into the rotor, and we could compute it with 3 I2 squared R2 on S, or TD omega S. Notice very importantly that when we work with TD omega S, there is no 3. This is not a per phase system, because this is the actual torque developed by the machine. It took 3 phases to give us this power to develop this torque, but there is no phase associated with the torque. So this TD by omega S is for the 3-phase machine as a whole. So you don't have to go and multiply by 3 if you have the developed torque. You don't have to multiply by 3 in order to get the 3-phase developed torque. It is understood that it is the torque for the whole machine. So once you get past the air gap into the rotor, you're going to have some more electrical losses on the rotor side, which you could find by using your equivalent circuit and saying I2 squared R2, or if you have the air gap power, you could simply multiply by S, the slip, and that is the portion of the power which is lost to heat in the rotor. And the remainder of the power, which is called the developed power or the electromagnetic power, again you could find it by saying, by just looking at your equivalent circuit and saying I squared R, or you could say 1 minus S multiplied, if you notice this entire thing here is this up here, so you could say 1 minus S multiplied by the air gap power, or you could say TD by omega, and notice this omega is not omega S, right? Because omega multiplied by 1 minus S, we have omega S here. When we multiply by 1 minus S, it becomes omega. So this is the actual mechanical speed of the rotor. And now that we have this mechanical energy being produced, some of it goes into friction and windage, and then the remainder, and this is usually a constant, this is usually treated as a constant, and the rest of it goes to the output, and this is your horsepower that you have here, and this is the shaft torque. So, in summary, by now you should be able to describe the power flow in a three-phase induction machine, and you should be able to calculate using your equivalent circuit the output and loss power in the machine. And again, once you keep in mind that equivalent circuit, the power is the same as you'd calculate in a normal circuit, I squared R. All you have to do, let's just go back, is remember that this is the mechanical side here. This represents the mechanical power. This is the rotor losses, stator losses, core losses. But once you know this part here is the total mechanical power, you could get what the shaft torque and so on is. Just remember that this has in it the friction and windage power as well as the load power. So next time what we'll look at the torque speed relationships in the induction machine.